All right, we have another integral here from Caltech Math Meet 2024, number 12. It definitely makes me think of reverse product rule, but it's not really clear how all this is going to work. I think for the first step, I want to break it up, but it's not really clear. Like, do I break it on this plus sign? Do I break it on this minus sign? I'm not sure how to group it. The first thing is to keep in mind, though, when we do it, we're going to want like derivatives of different things. So it's like, nothing really works. Like the derivative of tangent is going to be secant squared. So it's like, I'm not really seeing how like this is going to relate to this unless I just use an identity on tan squared x. That's going to be the same thing as secant squared x minus 1. And then just by doing that, we notice the derivative of tangent is secant squared. The derivative of minus x is minus 1. And so that's going to give me the way to break this out. We'll rewrite the integral. We'll keep it all in one integral. We're distributing in e to the x. Then on this first part, we'll write it like e to the x, tan x minus x. And then we'll distribute in the e to the x just to this right here. So we're going to have plus e to the x secant squared x minus 1. And then we'll start to label things. I'll just take e to the x, and I'll call this f. If I take the derivative of it, I get e to the x again, right? So then come over here, and here's our f prime value. So we have those matching like that. But then coming over here, we have this set up from just what I did right there. So use another label. We'll call this thing here g. Take a derivative of tangent, secant squared, derivative of minus x minus 1. This is just g prime. Quick review of the product rule. When we have two things, f times g, and we take a derivative on this, what we get is f prime g plus f g prime. That's exactly what we have here and here. The whole thing's in an integral, right? But when you have a derivative inside the integral, what comes back is this is just going to be the same as fg plus a constant. So what we've done is we basically set it up where we can go to our solution. We're saying we want to pull back the f value and the g value. So that's going to be e to the x times tan x minus x. We just need to, in this case, it's a definite integral. So we just need to evaluate it in order to finish it. So we plug in 1. We're going to have e to the 1, which is just e. We'll leave this as tan of 1 minus 1. Plug in a 0. Well, everything here is 0, and that's going to be a 1 times 0, so we'll just leave that off. Now, the interesting thing here is when I first did it, I'm used to seeing like 1 for arctan, so I was like, oh, this is pi over 4. But that's actually wrong. This isn't arctan, that's just regular tangent. So regular tangent at 1, I don't know what that is. That's a decimal. We probably need a calculator for that because, you know, for tangent, we know how to calculate pi over 4, pi over 3, pi over 2. I mean, even though that I know some of the values are infinite, but tan of 1, I don't know what that is. So what we'll do is we'll just circle it and call it good. And that does match what they have in the answer keys, so you don't need a decimal for it. It might just be interesting. Maybe I'll post it on the screen if I figure out what that is. And again, going back to this, there's a few different ways. You could do integration by parts on it, just maybe picking. I mean, clearly you can split this up into multiple integrals, 2 or 3 integrals. So I don't know which one works. I didn't do it, but some combination, integration by parts, and that should get you to the same place. Okay, that's it for today. Thanks everyone for watching. Have a good day.